So we're going to cover some basics of differentiation. We'll start with the derivative of a constant and then the power rule. So the derivative of a constant, if we have f of x is equal to a constant c, then the derivative with respect to f and the derivative with respect to c is equal to 0. So an example of that would be the derivative of f of x is equal to 3. So what I know is that the derivative of f of, with respect to x would be, the derivative with respect to x of this 3 is going to be equal to 0. That would work for any constant. So say if this was equal to 5, well then the derivative with respect to 5 is also 0. Now it's easy to show graphically because what we're talking about is we're talking about a horizontal line and y is equal to 5. And the derivative represents the slope of that equation at every point. You can see that the slope of this line is equal to 0 at every point. Now the power rule is something we're going to use all the time. So if f of x is equal to x to the n, where n is a real number, then the derivative of x to the n is equal to n times x to the n minus 1. So I want to determine the derivative of f of x, which is just x to the 4th power. So the derivative with respect to x of x to the 4th, what we do is we take that power, we bring it out front, and then we drop it by 1. So this is going to be 4x to the 4 minus 1. So this is going to be 4x cubed. Now I'm going to do some different variations of this power rule in just a second. So here are a couple variations of this, of different functions that involve the power rule. So I just rewrote it up here, n times x to the n minus 1. So if I have x to the 7th, I want to take the derivative with respect to x of this function x to the 7th. What we know is that power is going to come out front, and then we're going to drop it by 1. So 7 minus 1 is going to be 6. Now this function still involves the power rule because I can rewrite it as, or in this form. So I could rewrite g of x to be equal to x to the negative 6 power. So if I want to take the derivative with respect to x of x to the minus 6 power, we know that that power is going to come out front. So this is going to be equal to minus 6x to the, now we have to drop this power by 1. So dropping it by 1, negative 6 minus 1 is going to be negative 7. Now most books want you to rewrite it back in the family where it came from, this being rational, so let's rewrite this as a rational expression. So this will be equal to negative 6 over x to the 7th. So this is going to be equal to negative 6 over x to the 7th. Radicals show up a lot as well. So again, this can be written as a variable to a power. So this is the same thing as x to the 1/2 power. So if I want to take the derivative with respect to x of the square root of x, or x to the 1/2 power, what we're going to do is we're going to bring that power out front. So this is going to be 1/2 x to the, now we have to drop that power down by 1. So 1/2 minus 1 is going to be negative 1/2. So to the 1/2 minus 1, so 1/2 minus 2 over 2 is going to be negative 1/2. Now again, we like to rewrite it back in the family it came from. So 1 is in the numerator, 2 is in the denominator, and this variable is also in the denominator because it has a negative exponent. So what I could write this as is 1 all over 2, that's square root, but in the denominator, so root x. Now we'll do one more that has to do with, kind of the mixture of these two problems. So let's say D. What if, say, f of x is equal to 1 over x, 1 over the cube root of x? Well, again, what we want to do is we want to rewrite this in this form as x to a power. So f is the same thing as x to the minus 1/3. It's a cube root, so it's a 1/3 power, but since it's in the denominator, it's a negative 1/3. So there's our f of x. Now I need to take the derivative of this thing. So the derivative with respect to f of x, or you can say df dx, is going to be the derivative with respect to x of this x to the minus 1/3. Bringing that power out front, this is going to be negative 1/3 x to the, now remember I have negative 1/3 minus 1. You have to drop it by 1. So negative 1/3 minus 3/3 is going to be minus 4/3. Now I'd like to rewrite it back in a radical form. Now we know that this is still a negative expression, so it's negative. This 1 is in the numerator, the 3 is in the denominator, and this base is in the denominator because it has a negative exponent. Now the denominator is its root for its rational exponent, and the numerator of that rational exponent is going to be its power. So it's negative 1/3 times the cube root of x to the 4th power. So I got another rule for you. I'll write it up on the board. So the constant multiple rule. So if u is a differentiable function of x, then the derivative with respect to x of c times that function is c times the derivative of that function. Now, what I want to do is to determine the derivative of something like a 5 times x squared. So what this allows us to do is if I want to take the derivative with respect to x of 5x squared, I already know how to take the derivative of x squared. You know, we can use that power rule. But what this rule says is I can pull out that constant and take the derivative with respect to x of our x squared. So we're able to pull out that constant. Now I can take the derivative with respect to x squared and then multiply by that constant last. So this is going to be 5 times, well, the derivative with respect to x squared is going to be 2x. And now I can multiply last, so 5 times 2x is going to be 10x. Now, another one might be, say, f of x is equal to 4x to the 5th all over 3. So if I want to take the derivative of this thing, I know that that 4/3 is a constant. So I'm going to take the derivative with respect to x of 4x to the 5th over 3. Means I can pull out that constant of 4/3 and then take the derivative with respect to x of x to the 5th. So this allows us to use that previous rule. So the derivative of x to the 5th is going to be 5x squared, so this is 4/3 times, 5x to the 4th. And now I can multiply last, so remember this is 5 over 1, so 4 times 5 is 20, and then 3 times 1 will be 3. So this is going to be 20x to the 4th over 3. Now, some other variations. Be like f of x is equal to, say, 9 all over x to the 7th power. So this kind of takes advantage of what we did before, that I can rewrite this x to the 7th in the denominator as 9x to the negative 7. So if I want to take the derivative of this thing, the derivative with respect to x of, this function is the same as the derivative with respect to x of this function is going to be 9x to the negative 7. I can pull out that 9 and then take the derivative with respect to x of x to the minus 7. Now this derivative is going to be 9 times, well, the negative 7 is going to go out front, and then we're going to drop it by 1, so x to the minus 8. And then we can multiply last. So 9 times negative 7 is going to be negative 63. And this is going to be x to the negative 8. Now, that means I have an x to the 8th power on the bottom. Now, we tend to start, doing this a little more quickly. So I know that I'm going to be able to multiply last. So if I want to take this thing's derivative, I really can just do 5 times 4, which is going to be 20. And this power is going to turn down to the 4th power. So I already know it's going to be 20x to the 4th over 3. And same thing here. If I'm going to take the derivative of this, I know that negative 7 is going to be multiplied by that 9, so I'm going to get that negative 63. And this negative 7 is going to drop by 1, so I'm going to get it to the negative 8. So this is minus 63x to the negative 8. And you'll start doing that quicker without having to, pull out that constant every single time. So last rule in this lecture is going to be the derivative of a sum. So if u and v are differentiable functions of x, then the sum is also differentiable. And the rule for that derivative is the derivative of the sum is going to be the sum of the derivatives. So the derivative with respect to x of u plus v is going to be the derivative with respect to x of u plus the derivative with respect to x of v. So what I want to do is I want to take the derivative of the sum. So what is the derivative of x cubed plus 5x? So if I want to find the derivative with respect to x of x cubed plus 5x, we know it's going to be equal to the derivative of the first term plus the derivative with respect to x of the second term. So the derivative with respect to x of x cubed is going to be 3x squared, and remember that this is a 1. So the derivative with respect to x of 5x, so this would be 1 times 5, so this is going to be 5. And what I'm going to do is I'm going to drop that power by 1, so this is going to be x to the 0. So 5x to the 0, x to the 0 is 1, so this is going to be equal to 3x squared plus 1. So I'll do a couple variations of this rule in the next couple examples. So with the derivative of the sum rule and the power rule, it allows us to take derivatives of polynomials really, really quickly. So if I want to take the derivative of this function, I know it's going to be the derivative of this plus 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 the derivative of this. And it's a little redundant to write derivative everywhere. We just know that we're going to use that derivative of the sum rule. So the derivative with respect to x of our x to the 4th plus 8x cubed minus 2/3 x squared minus 4x plus 1 is going to be the derivative of each one of these terms, or the sum of those derivatives. So the derivative of x to the 4th is going to be equal to 4x cubed. The derivative of 8x cubed, well, we know we can do this quickly. This is going to be 3 times 8, which is going to be 24. And I have to drop that power by 1, so this is going to be x squared. Similar here, this is going to be 2 times negative 2/3. So 2 over 1 times negative 2/3 is going to be minus 4/3. And then I have to drop that power down by 1, so x to the 1. The derivative of minus 4x is just going to be minus 4, because it's going to be, this 1 here is going to be minus 4. When you multiply the power times the coefficient, you're going to drop that power down by 1, which is going to be x to the 0, which is 1. And then the derivative of a constant is equal to 0. So we're done. Similar in form, except you have this rational term here. So if I want to take the derivative with respect to x of this sum, x cubed over 2 plus 4 over x, well, it'd be much nicer if I write that 4 over x, so I can do it using the power rule. So this is going to be, what I would like to also do is rewrite this. This is 1/2 x cubed plus 4x to the negative 1. When you're using these power rules, it's nice to isolate your coefficient, your variable, and then your power. So coefficient, variable, power. Just like you have here. Like this is nice and isolated, so it's easy to take its derivative. Not so much there. So I can see that the coefficient is 1/2, and then this coefficient is just 4. So now when I take its derivative, 3 times 1/2 is going to be 3/2. Drop that power by 1, so x squared. And negative 1 times 4 is going to be minus 4. And I have to drop that power by 1, so this is going to be x to the negative 2. Now I do like to rewrite them back in the family where they came from. This came from a rational expression, so let's rewrite it as a rational. So this is going to be, I could even combine this too as like 3x squared. 3x squared over 2 minus 4 all over x squared. It's not necessary. You could just leave it like this. This is fine. But it looks similar to where it started. Now you might ask, like, you said it was only the derivative of the sum, but remember that differences are just sums of opposite numbers. So what works for the sum is also going to work for differences. That's it.